the rough, oh, there we go, recording. So I think the rough plan today is I'll talk for a while about some of this. I'm going to start by asking you a few questions too, just to find out where you're at. And we'll have a chance for some discussion. If you've got a question in the middle of me going through some of the things, do maybe type it in or something like that. And if I completely miss it, Tracy can jump in and yell out and let me know, because it is good to deal with things as they come up. But yeah, so we're going to be talking about computer graphics for level three. It'd be really useful just to ask a couple of questions to know where you're at the moment. And so, first of all, I guess, could you just type in a yes or no into the chat, whether you've taught this before, computer graphics at level three or some form of computer graphics? Cool. Okay, so excellent. So, oh, yep, great. We've got a couple of people there, a few people who've done some of it, which is great. It's um, and I hope we can sort of draw a wee bit on our collective experience because I'll talk a bit about the whole big picture of things. I'll give a few specific examples, but I have had relatively little experience teaching this in the classroom. I've had some experience, but there are people here who will have no doubt taken it and made it much more learnable than I would too. So let's share some of that goodness. Now the other thing is, and those of you who've taught it are probably aware, but I think it's quite useful to know where you and your students are with mathematics because it is quite a mathematical subject. And I think it's one where if students are into mathematics, it's like, oh, this is just so clear and straightforward, and I know what I'm doing. And if their mathematics, if they've been avoiding mathematics all their life, then it's just probably going to freak people out. So I guess it would just be good to know, and I'll let you collectively say you and your school, yeah, whether the mathematics is something that will probably help or hinder, or would, for a lot of people, it might just be a bit of a challenge, but it'll be worth it. Yeah, okay. So matrix multiplication. Okay. Yeah. Okay. Cool. Yeah, but bimodal, yeah, some kids will love it, some won't. And there are, of course, three options for the standard. There's graphics, complexity, and tractability, which also has a moderate amount of mathematics in it, but it's got a few more actual numbers in it, where you're talking about how long things take or how many times something will happen. Um, and then computer vision, which actually is just computer graphics in reverse, and that I think it tends to not be presented quite so mathematically, but to really do well on computer vision, it is also quite mathematical as well. Um, Now, I mean, when we talk about maths, we're not talking about really advanced ideas. And I think what we've done so the computer science field guide is something that we're going to use um, quite a bit, is we've tried to really break the maths down into pretty straightforward things. So the main thing, even though we talk about words like matrix multiplication, the main thing that they really need as a prerequisite is working with coordinates. An X and Y coordinate. X is how far across, Y is how far up. And we can grow everything from that. And so hopefully that is a reasonable starting point for students. It's certainly way before level three mathematics. But yes, it will be a little mathematical. Let me see if I can share my screen and get back to. Sorry, it just takes a while to rearrange the details once I do the share. Okay, so hopefully someone will yell out if you can't see that. Okay, but that's my title slide. And in actual fact, one of the things, in fact, I'll just put up my second slide. I did put this in the chat, but I've created a Google Doc page where we can all collectively take notes. In fact, I'm just going to open it up for editing. So anyone with the link can edit, which means we can all take notes on that page if you want, which would be good. I've put a few links in there of things that I'll be talking about. But To sort of get things started, we do have a video on the field guide, which is one of the first links in there, and this is actually one of our students called Rem, and I'll just play a little bit of it, but some of you will have seen it, but it does kind of give a good overview. So I'll let Rem do some speaking. Um, Maybe, and Tracy again, just type something in the chat if this isn't coming out correctly.
Computer graphics is used to create all sorts of images. But at the end of the day, they're just pixels that are being given a certain color value. Computer scientists who work on computer graphics work out how to take an object, do some calculations and translate that to a computer screen. For example, we need to think about an object's rotation, its position in 3D space, and its size. This also involves specifying colors mathematically.
Okay, so I'll just stop Rem there, but that's kind of a lot of it, and hopefully the graphical illustration of that will give you an idea of where we're heading. So the standard itself is here. It's interestingly, it's planned for review in December 2020, so we'll look forward to that. Uh, I guess that means it stood the test of time. It's still there. And the assessment specifications for the standard, they're available online, but basically it's an exam. It's an online digital exam, so kids are, I think they're basically typing into boxes on the screen, and it will be one of those three topics that I mentioned earlier. Uh, and there are a couple of notes here that are worth noticing. So one is that you're encouraged to help students develop answering techniques because they will be asked to just do general discussions about the area they've chosen, in this case, computer graphics. Encouraged to help students prepare to apply it to unfamiliar contexts. So they may be given a new situation and obviously apply it to that. And it's easier to articulate ways that it might overlap with other areas of computer science. Now, I don't think, well, in some ways you can't help that because everything in computer science overlaps. In NCA and in the computer science field guide and in any courses, there will be distinct topics on, graphics and vision and AI and algorithms and that. But really, all of them use each other. And so you will find that inevitably they will be looking at algorithms or performance or things like that. Um, the big picture, and this applies to everything in the standard, I think, one is to be aware that hopefully the students have a foundation from previous years. And if they haven't, I think that can be a bit challenging for students because occasionally I've seen classes thrown straight into level 3 computer science without having done any programming or previous computer science standards or anything like that. And while it doesn't directly use things from that, to come in cold, I think, is very hard work. The other thing is a big picture is that it's not so much that students need to know particular things about graphics or whatever the topic is that you've chosen to look at, but it's actually just to build excitement, or at least have the students know what the topic is, because I think um, before NCA was doing this, we had a lot of students turn up, had no idea what computer science was, what they'd be doing, and so on. And we've noticed a real difference now. Students are arriving with a purpose and they kind of know what's involved. Students doing computer graphics know that there will be mathematics in it, not that they'll be playing games all day, things like that. So, computer graphics. I'm going to just spend a couple of minutes talking about the general field of computer graphics. And so first of all, probably a lot of your students, when you say graphics, they might think of a game, probably involved running around shooting things or something like that. And yes, that makes heavy use of computer graphics. But also films, actually possibly even more demanding use of computer graphics. And Weta have won, amongst other things, Emmy Awards for graphics. We've got graduates from our department who have Emmy Awards because they wrote computer programs that developed new graphical systems. And so, there's definitely cool stuff to be done there, not just writing games. And then even if you look at software like Blender and anything that's working with graphics on the screen, someone had to write that software, and they're using the techniques from computer graphics to do it. And this also emphasizes what we're talking about. We're talking about knowing about how you, not how you would use something like Blender or graphics editing, but how you would write the software for that. I mean, students won't be writing a new version of Blender, but it's knowing what's happening behind the scenes so that these things can create three-dimensional graphics and so on. Now, most of what happens in computer graphics is what we would call rendering from models. And if you can see this, there's a model is just a bunch of objects. Here we've got a red cylinder and a yellow sphere and so on, that someone's decided they want in this picture. And almost all the graphics that you're likely to work with, without getting too complicated, are likely to be fairly simple like this, or at least we'll use them for examples. And so those objects, they have a size, they have a place in three dimensions, they have lighting on them, and all of that's done by people. Well, the things I put on the right, either you specify it, like you say, I want a circle at this place, or I want a face, or I want hair on this head over here, or something like that. Or it could be scanned, and I want the scanned thing placed here on the screen. Could be motion capture, where you've tracked people and you say, I want this object to follow where this person's moved. It could be games, which are generating positions as things move around in three dimensions. It could be from photos. Sometimes people take lots of photos. I just heard a report yesterday. Someone took 2,000 photos of a coral reef, and then it was reconstructed as an image in three dimensions from the photos. And it could be 3D software like Blender and so on, where you're actually building things. So you've got this model, and the model is inside what's referred to as a frustum. So there's one big word for the day that you can use with students, which is just, well, perhaps I'll go the other way. You have the camera, often it's shown as an eye, that's the person looking at it, and the view plane, which is actually the screen that it's on. And that screen, it might be a computer screen, but it might be a screen in virtual reality glasses or something like that. But inevitably, it's going to be a two-dimensional screen, because in the end, the eye perceives two-dimensional objects, and it's 3D by putting different things into each eye. So so you've got your view plane or screen, and then this frustum, which is where all the objects are. And then you've got lighting, and because actually without lighting, nothing will be visible. And the whole goal is basically we've got all these specifications of where things are, and we need to put it onto this two-dimensional position here and make it look realistic. Okay. So what is computer graphics? Well, writing the software that generates graphics, or alternatively turning digital representations into pixels on a 2D screen, or using maths to create images. And we have to be realistic. There is quite a bit of maths in there. And there are many elements to computer graphics to look at. And we'll look at the specs in a wee bit, but just to give you a bit of an overview, drawing lines. It is just hard to draw lines, and we'll spend a bit of time on that because it's an interesting thing to do. Rendering, where you've got the specification and then somehow turn it into colors on a 2D screen, but then what about adding lighting and shadows and things like that? So rendering is taking the description and the software that takes that description and turns it into something that looks realistic. Animation, where things actually move around, not so you haven't just got objects, but they're moving. Lighting, so there's a picture of a sphere, because of course if you don't specify any lighting, it will just be a black sphere. Now the sphere has some color or brightness to it, but actual lighting will, the actual color will change across the surface of the object, and that gives it a sense of dimension and so on. And so just applying lighting to things is really hard work. In fact, if you look at any film, any animated film, Avatar or Shrek or anything like that, get students to look at the number of people who have been involved in lighting. All of that lighting is entirely done by software, and yet normally there are dozens of people just doing the lighting for it. Anti-aliasing, where because everything is going to end up as pixels, we want to have it so that if you've got a line that's straight, it doesn't look too blocky, and so there's tricks that can be done to make sure that doesn't happen. And then transformation we'll spend a bit of time on too, moving things around on the screen, like Rem was doing, making them bigger, smoother, move around in three-dimensional space. Um, and then hidden surface removal. How do you actually show that one thing is behind another thing? And yeah, and there are algorithms around that are needed to be able to make sense of that. And of course, tied in with all of this is however it's done, you want it to work really, really fast because typical graphics, you've got 24 frames or more a second being displayed on the screen. So it's got 1/24th of a second to calculate several million pixels. And so, you don't want to do any unnecessary calculations in the process. Ray tracing is a technique that makes for really realistic images. I'll talk about that briefly later on. Clipping, because when you specify where an image is, the screen itself, that green part, might not include the entire image. So how does the system work out which things to show and which things not to? And especially not to spend a whole lot of work showing things outside of the screen that are never going to be visible. And then there are graphics languages, and one of the ones that's used a lot, it's been around a long time, is called OpenGL. It's possibly not the best one now, but it's still used a lot for teaching. There's a lot of teaching resources for it. And so if your students really want to get their hands dirty and do some programming, not totally necessary for this, but I think it does help a lot if they've actually tried doing that, then OpenGL is pretty available and a lot of teaching resources for it. It stands for Open Graphics Language. And there's a variation of it called WebGL that will work in a web page. Projections, which people have done tech drawing and so on will be aware of that where you've got a viewing point, things that are close to the eye are bigger and things that are further away are smaller and things like that. And so there's a whole lot of mathematics around projections and lots more texture matting, shadows, morphing, computational geometry, painting, motion blur, and so on. But I just wanted to sort of set the scene that there is a lot that you could look at in computer graphics. You do not have to look at all of that. And in fact, you probably want to focus on these things because the assessment specifications say that what it will be doing is covering bitmap and vector graphics. And by the way, I'm going to go through each of these: matrices, transforms, line and circle algorithms, image rendering, and texture mapping and lighting. So we'll have a look through those, but hopefully I've sort of set the context a wee bit there. Maybe I'll just pause, take a breath, and are there just any questions about the big picture, the general things so far? Just note Nari's comment. Yeah, level 3 boys who discovered that engineering requires programming. Yeah, yeah. I think it's probably the case in Auckland, but certainly at Canterbury, every engineering student has to do a programming course. Yeah. Well, I'll move on in the absence of any comments. Um, so, I'm going to start with line drawing, and partly, well, it's in the spec for this year. It's been in some of the past exams, and by the way, past exams are available on the TechReady website, so that's quite good. I wouldn't get your students to learn how to answer exactly those exams, but they do give a feel for the kind of things that students would the level at which they need to be able to do things. And one of the things is that generally there's resources are provided in the exam that, particularly where there's mathematical formulas and things like that, they seem to provide most of the formulas. So it's not so much about memorizing formulas, but having a sense of the purpose and so on. So drawing lines, well, no, not most, yeah, probably most graphics actually, it breaks things into triangles. So whether it's a face or a car or a gun or whatever it is that you're rendering, or a blue character in a animation, chances are that they are being modeled by lots and lots of tiny triangles. And those triangles, of course, have three lines. And so the ability to work out where the points of a line are is really important. But even just in a simple drawing program where you use the mouse and you click and drag it and it draws a line or a box or something like that, the computer needs to work out how to draw a line. And in fact, I'll just switch to the field guide for this. And there we go. There's a whole section on drawing lines. And so the point is that if you're given two, well, yeah, if you're given if I click on here and here, and the computer has to draw a line between them, actually a fun challenge for your students is to work out, well, which pixels should I color in? And that doesn't look like a straight line. And it's actually quite hard to do it by eye. Um, and but the job of line drawing is simply to work out which pixels do we cover in to make a straight line. Now, a straight line isn't actually a straight line on a computer anyway. It is just a bunch of pixels. And so in the field guide, we've got a challenge here for students to try and draw the pixels between A and B. And then just place a ruler on the screen and see if all your pixels are underneath the ruler. Now, the thing is that for a human to draw a line, it's real easy. You just get a ruler or squint your eye and just draw the thing. But for a computer, it has to calculate which pixels to color in. And if your students have done any basic mathematics, they have probably seen this formula here, y equals mx plus c. That's the formula for a line in mathematics, which just means that, so actually one thing that comes up over and over in graphics, so x is going across the bottom here, the x-axis. So this x is going from 0 to 19. So that particular pixel there, its x value is 7 and its y value is 1. So y is going vertical. And with three-dimensional graphics, we have X, Y, and Z, which is going in and out of the screen, the Z. So we're going to stick to 2 dimensions for a lot of this, because all the ideas in 2 dimensions will transfer to 3, except it's a bit less to get your head around. So basically, this formula here, mx plus c, means that if x is 5, so m tells you how steep the line is, so maybe m is 2, the line has got a slope of 2, and c is basically the starting point. So suppose it was 2x plus 5, then this one would be should be at 2 times 5 plus 5 is 15, and the next one will be at 2 times 6 plus 5, and the next one's at 2 times 7 plus 5, and so on. And so it will be going up in twos, and it will be 5 above the bottom line here. Now, that probably students knew that and they've chosen to forget it, but that is a pretty straightforward formula. The trouble is that for every pixel, you have to multiply 2 numbers, and generally these are going to be real numbers. Then, so computers often generally store integers or whole numbers, or they store real numbers, which can be fractions and so on. And when you're doing this formula here, it's actually really slow because multiplication is slower than addition, and real numbers are a lot slower than integers. So it's actually really just wouldn't work, the standard formula that mathematicians use. So enter Bresnam, who came up with a really clever way to calculate exactly the same line from between 2 points, but it only uses integer calculations, and it only uses addition and subtraction. And subtraction is basically addition as far as the computer is concerned. So it's really fast to do. And since there are often millions of lines to draw just for a simple image, it's actually quite a good idea to use a fast algorithm for that. And so I won't go through the details because it'd just be boring in this situation, but basically you have x1 and y1. So A here starts at position 3, x is 3, y is 4, so it's at 3, 4. And B is at, so this is x2 is 16 and y2 is 9, so that's where that is. And once you know those values, you just pop them into this formula. So y2 minus y1, well, y2 was 9, y1 is 4, so y2 minus 1 minus 4 is 5, and multiply that by 2. So A is 10, job done. This is x2 minus x1, you could calculate that, and you'll have a value for B, and for P. And that's done before the line is drawn, and then the computer, or your student, if they're doing it by hand, applies the simple rule. If P is currently less than 0, then draw the pixel on the same line as the last pixel, so it just goes across from A, and add A to P, which will change P. And then the next time round, if P is still less than 0, we stay on the same line, but if P is 0 or greater, then it will go up a line on the next one. And so P is kind of keeping track of whether you're kind of a little bit below or a little bit above where the line should be. if students do this a few times, they'll pretty quickly get a feel for how it works. And in past exams, you'll see that generally students have been asked to calculate the points in a line, and they're typically given this formula. There's a couple of different ways the formula can be written, and I noticed that they tend to give the two different formulas. They do exactly the same calculation. It's just a slightly different way of writing it. So that's Bresnam's line drawing algorithm. Might stop for a minute. Maybe if anyone want to jump in, if you taught this, have you got any ideas that help students with it? Oh, okay. Keep getting it wrong. Yeah, it's easy to make a mistake as you go along. Yeah. Um, was it just the actual calculations with the numbers, Steve?
Yeah, I actually tried to write a Python program to do it
Yeah.
to make it easier.
Actually, it's a nice little Python program. It's only about 5 lines, eh? And yeah, it's generally a good idea to get computers to do it. We only get kids to do it because it forces them to understand what's going on underneath. Yeah. Yep, computer file is great. I've put a couple of links in there, but actually, Ruth, if you've got some other videos on YouTube that you use a bit, feel free to drop them into that document. Just towards the end of the document, there's I've got a few things by computer file. Yeah, they tend to do a slightly humorous, well, I don't know, fairly down to earth take on things. Yeah, cool. Um, okay, and I won't go through this in great detail. The field guide's got a lot of stuff here. By the way, one just slight side topic. One thing I've been doing, I mean, we find that we get some students who just can't read lots of text, and the field guide itself seems like a lot of text to the students. I'm sure if we turned it into a graphic novel or something, it would be a lot more approachable. But one thing we've done lately is drop things into Google's Notebook LM, which turns it into a chat between two people, and so it restructures the information, and it's a chat. I don't know if anyone's done that, but that may be a way. It sometimes makes little mistakes, but it generally is pretty accurate. And some students who are not into reading might get as much out of that as they will staring at things working on, floating around on the page. Oh, Excel, yep, another great way to do it, actually. Thank you. Yeah, yep. Um, cool. It just forces them to think, what is X1? What is X2? Because it's not that hard. It's just exactly where the pixels are and so on. Cool. Okay. Um, Circles are also in the specification, and so they're pretty straightforward. A circle has got a center and a radius, and the challenge here is to work out which pixels are going to be colored in. I'm just guessing here; these are probably incorrect. To make a circle around that center, that's terribly wrong. And so very similar kind of thing. It's just a simple calculation, calculate a few values, and that will work out. Normally, I'll go back to my PowerPoint. If you're calculating circles, it's about the radius, and to get the XY coordinate. And in fact, that's a right angle triangle, and the formula is Pythagoras's formula: r squared equals x squared plus y squared. So it's an actual, it's a very real application of something that students may have thought was just something mathematicians made them learn for no particular reason. And I will say one thing about graphics is it definitely makes a lot of mathematical stuff, very useful. And by the way, um, circles are symmetrical. They have 8 symmetrical parts to them, or octants. So once you've calculated this pixel up here, yx, you know that the xy one will be the same, and x negative y and y negative x and so on. So that's just another fun thing about, there's actually very few calculations needed. You just got to work out 1/8 of the circle, and you've pretty much got the whole circle. Very fast way to calculate circles. So, next time you drag your mouse to draw a circle in PowerPoint or anything, think about good old Bresnam's algorithms in behind there, making it happen really fast instead of, doing a 10-second calculation between every new circle that it draws. Okay. Right. Um, and the next sort of concrete thing, and the main other mathematical thing in there is the transformations. And basically, it's the motivation is in that video that Rem did, where he had the duck, sort of moving left and right and in and out of the screen and up and down, and then getting bigger and so on. Now, the way we've done this in the field guide is we've got a bunch of interactives here, and I'm interested if anyone's used these, but what we do is, like, for scaling, here's all the XY coordinates of this picture of the number 7. So each of these dots here is just an XY coordinate with a line between it. We know how to draw lines using Bresnam's algorithm. And so this -2, 3 coordinate is, 2 to the left and 3 upwards from the center. It's that one there. And we've asked people, the students here, just to multiply every value by 2. So instead of -2 times 2 is -4, and 3 times 6. And as soon as they type it in, it's moved that single point up there. So now, basically, it's twice as far up and twice as far across as it was from there. And if we do this to all of the coordinates, -4, 2, and double that one there, and so on, we're gradually making this 7 twice as big. Okay? And so the idea is for students to see exactly what's going on behind the scene. The other side of this activity is to say, this is really tedious, changing every single coordinate. And so eventually that motivates us to use matrix transformations, where we just have 4 numbers, and the top left-hand number here in the matrix says multiply every x value by 2. Done. And the bottom right-hand one says multiply every y value by 2. Done. And I've just made that image twice as big. If I change that to, I don't know, 4 and 4, that means multiply every x and y value by 4. In other words, it's been expanded 4 times as big, it's 4 times as wide, 4 times as high. And if we change it to a half and a half, then all the XY values have been halved. Way easier than doing it all by hand. And that's one of the key reasons that matrices are used. And what this really meant when we had the 2 in here is it says, for your x values, take 2 of the old x value and none of the y value. And for the y values, take none of the old x value and 2 of the y value. So it just says how much of each x goes into the x's and how much of each y goes into them. Which means, if I do it the other way around, if I say take the x's are going to be none of the x values, but say 2 of the y value, and the y value is 2 of the old x's, then I've flipped the x and y's, which means what used to be up and down is now left and right, and what used to be left and right is now up and down. And that's rotated it. And so now we can see, it's sort of, just by playing around with it, you can see how those 4 numbers in a matrix can rotate things, they can make things bigger. And there are only 3 main things that we really worry about too much, which is rotating them, scaling them, and moving them around on the screen, which is done separately. There are a few other transforms that get used in heavy-duty graphics, but that's basically what there is in a matrix. So we've tried to sort of unpack the mathematics into just actually using numbers and so on there to experiment with it. So I will just maybe pause for a second and see if there are any questions or sort of korero around matrix transformations and so on. Okay. Now, the way it looks when you write it out can be a bit scary for students. There's the 2002, which means make it twice as big. There's the coordinate 2, 3, and there's the result of it. The point is going to be 4, 6.
That'll have Tim. Just a question about what they'll be examined on. So it is in the exam. I'm just wondering if there's a conversation there about what kind of, have people seen that presented in exams in the past, so they can and not practice for the test, but have enough understanding and practice in that space.
Mm. I guess it sort of goes back to the specification, which is, here we go for computer no, that's not it. I can't find my own slide for that. Oh, here we go. So yeah, it just says matrices and transformations. I guess looking at things in the past, and maybe some other teachers who have done it will have a better idea than me, but I mean, it's not a mathematics test, and it's not testing that they can multiply millions of numbers and all that sort of thing and keep track of them necessarily. It's just that there's enough to be able to track that they understand the point of these things. And so I I think like in the field guide, we talk about scaling, and it would be, I think that would be a straightforward thing to talk about. We talk about translation, which is moving things left and right, which by the way is super simple. You just add a number to each point, right? And rotation. And I don't think I mean, rotation starts to involve a bit more trigonometry than students might sort of use every day. And I don't think it gets emphasized too much. It probably doesn't hurt to know that matrices can do rotation, and they've had some experience with that. But for example, I don't think they would need to apply this formula, partly because they certainly wouldn't be expected to memorize it in the past. I think they've always been given formulas and so on. And also, it's, there's a lot of calculation to go on. You have to have access to a calculator to do that. And Nora's asking about 3D. I guess it would be good for students to be comfortable with 3D translation as well, 3D transformations. All it does is it's 3x3 matrix instead of 2x2. So like, to make the thing twice as big in every dimension, it's 2, 2, 2 instead of just 2, 2. And part of that is too, I think students 3D graphics look cool and all that, but you have to realize that it's actually a little complicated. Yeah. Sorry, just reading the things. Yeah, practicing it reinforces what's happening. Yep. And yeah, I think three-dimensional transforms would make sense. And Ruth point out, but probably not heavy maths. Yeah, just simple images like the T and the 7 that we had there and so on. I mean, for 3D, we've got this thing in the field guide. I don't know, it might be a bit hard to see on your screens, but it's just a teapot in 3 dimensions. And so, if I change the X to a 5, it's just going to make it 5 times as big in the X dimension. If I change the Y to a 5, it's now 5 times as big in the Y direction. But you notice if I look at the Z, I haven't made it bigger yet. I'll make that 5 times as big. And now, oops, no, I didn't. I put the Y into that, that'll rotate it. So click the apply button, and now I've just made the whole thing 5 times as big by putting in 555. I think getting into rotation there is probably getting a little quite fiddly in terms of the how that works. Oh yeah, and yeah, good point, Ruth. The harder part is often the implications, merit and excellence, and we'll come to that in a minute. But I think if they're using these things, if they understand what's going on behind it and what it's applied to, and observe it being used in other places, then they can start to make those connections with the implications, because they're starting to realize all the calculations that need to be done and so on. By the way, another reason that computer graphics uses matrices for transformations is that generally there will often be 6 or 10 or more matrices applied to every pixel, because it will have the size chosen and then another matrix to get it to the right position, and then another one rotating it a bit more there, and then another one working out where it is relative to the camera, and then another one working out where it is on the screen, all sorts of stuff like that. And all of those multiplications of the matrices they can be collapsed down into one multiplication, one matrix that does all of them. So once you know what say you've got 10 matrices to multiply, you can collapse them all down into one and apply that one multiplication to every pixel, which makes it super fast. So matrices really are a good way to, it's a preferred way of moving things around on a screen. I'll just quickly go through a couple of the other things. So it says that they should be aware of bitmap and vector graphics, which is generally pretty straightforward. It's bitmap or raster or pixels, basically, where an image is only stored as pixels, and if you take a small image and make it bigger, you just end up with bigger pixels. Whereas vector, it's the shape of it, it's specified mathematically as curves and lines and things like that. So if you make it twice as big, the vectors get twice as big. It's still a curve, and so it can still be rendered to look really good. And there's plenty of information around about the difference between those, but generally, JPEGs and GIFs and so on are raster, SVGs, and actually PostScript. PostScript can do both, but they store. Well, in fact, SVG is called scalable vector graphics. Yeah. So it's the difference between when you're enlarging things and so on, and that it just applies to something as simple as a font. One of the next topics in it is rendering. And especially ray tracing versus rasterization, and that probably does require a bit of understanding because, actually, let's look at ray tracing. So ray tracing is where you have a camera or the human eye that's looking at the thing, and you trace the ray through every pixel on the screen. So you just follow it, and so suppose I wanted to know what color should I make this pixel. Well, mathematically, you work out where that ray of light is coming from. So it's actually doing the lighting in reverse. And if there's an object there, you go through and you find that mathematically it intersects with the sphere. And if it hits at a certain angle, the way mirrors work or reflected surfaces, when you hit something at an angle, it reflects off at the same angle. And so mathematically, we can work out the angle it will go off. And eventually, it'll get to a light source. And so that tells us what sort of light will be on that particular point. So it's just going through everything in reverse. This is generally quite slow because for every pixel, you're working out where that hits and then where that's going to, where the light came from before then, which might be from another object, and then from before then and so on, which be from another object again. But what it does mean is you end up with very realistic images because things like glass and refraction and things that partially reflect and all that sort of stuff just work perfectly. You can specify lights anywhere in the scene and they will all work perfectly. Whereas simple rasterization, which is way faster, and what will normally happen if it has to be really fast, is basically works backwards. Each object, you work out where it is on the screen, work out if it's occluding another object. There's another good word for students to use. So this yellow sphere is preventing us seeing some of the blue pyramid here and so on. So you have to, there's algorithms for working out what's in front of what. Ray tracing takes care of that automatically because the ray will never get to something that's behind something else. But rasterization, you have to have algorithms for all this. Seems like more work, but it's actually a lot faster. Usually it's a lot faster. And I guess also behind the scenes with all this is these days we use GPUs, graphical processing units, which basically are very good at matrix multiplication and can do all these calculations really quickly. Fun fact, of course, is the GPUs now get used for all sorts of other things like mining bitcoins and for AI, because it turns out that those things all need the same kind of matrix multiplications. So probably notice every time AI or Bitcoin or something like that takes off, the value of GPU stocks goes up as well because they get used for that as well as for rendering images. So that's the ray tracing and so on. Texture and lighting is in there. And yep, computer file, they've got a great thing about light and shadows. And he actually illustrates it in a video using real lights and real shadows. And, I think one of the other things about graphics is it gets students thinking about the real world, like what is my perception of light and color and all that sort of stuff. It's, we take it for granted, but there's an awful lot of subtlety going on in the real world. Yeah, very cool. And then related to that with texture is, so these are both just mathematically specified as spheres, but they've used a texture mapping system, in this case called bump mapping, which just puts a few random bumps on top of the sphere, moves it in and out. So when light or when it's being rendered, yeah, it's basically only light, where the light hits it and so on. It puts in a few dark bits and so on. It makes it look like it's really rough and, made out of plaster of Paris. Although you notice the one on the left, actually, they didn't bother telling the lighting system about the bumps. And so it's a bumpy sphere with a perfectly round shadow. And the one on the right is a bumpy sphere with a bumpy shadow. Generally, when people are taking shortcuts and they need it to be fast, sometimes they just go, can't worry too much about that shadow. Nobody's going to notice it. We're going to, if it's a video game and things are moving around and so on, they won't bother. If, on the other hand, it's a beautiful picture that's going to be framed and put on the wall or used for advertising or whatever, you probably want to get all those sort of details right. Okay, so that's basically a hasty run through of the main topics, but and then just as Ruth was pointing out, for excellence and merit, it's sort of understanding that enough that you can think about the implications and think of new connections. And in the exams, they tend to just, they almost sort of sometimes ask questions that pretty much are um, straight from the standard in some ways. But um, what would be an implication of this, or make a prediction about that? What's an improvement for this, and so on. And I think those students that have really understood it and maybe even played around a bit with some programming, maybe even decided to have a go at OpenGL, although that's just to draw a circle in OpenGL takes half a page of code. But then to make that circle do fancy things doesn't take much more code. But there is quite a bit to get into before you program it. But if you've got students who really are operating at excellence level and thinking about how these things really work and what the mathematics is really doing, and what's fast and what's slow and so on, then I think if they're given, and it did say that they'll be given new situations, so they might be given some example situation and they can think about how different approaches might work better or worse in those sort of situations. So that is a quick version of it. Toy Story 1 versus Toy Story 4. Yeah, actually, it's just stop sharing so I can see your amazing faces. And in some ways, we are living at a point in history where these things are progressing a lot. GPUs are getting faster and so on. And so we are seeing stuff being done now that requires a ridiculous amount of computation, but it can be done on a desktop computer. Although then if you look at people like Weta Digital, who have done a lot of those big animated movies like Avatar and dozens of them, I'll put a link into their awards page because they've got so many awards for animations and computer graphics, that they will still often, well, you can look it up, but I think sometimes they will spend 2 hours rendering a 3 second scene. There's so much calculation going on, but that's okay because they can spend a month or two rendering a movie and then people will go and watch it in 2 hours. That's fine. But these are some of the implications that your students need to be aware of. It varies so much. If you're a movie outfit, you'll put the time and effort in. If it's a real-time game, it's just got to look good on the screen. People are too busy playing the game to notice every little detail. Yeah, so all these different sort of trade-offs that can be made. Yeah. Oh, okay. Yep. The 3D scanning of the Titanic. So, and in fact, the scanning itself is, I guess, computer vision, which is another topic. But then rendering the scan is the graphics part. Yeah, where you've got a 3D, and actually pixels when they're in 3D are called voxels, which you possibly know, volume pixels or voxels. And so, yeah, you can end up with a lot of voxels, but then how do you store voxels and all that sort of stuff? It's a whole area of graphics to get into. Actually, the other scanning, of course, that's almost as interesting as the Titanic is medical diagnosis, where you find lumps and bumps in people and things that shouldn't be inside their bodies and all that sort of stuff, and accurately target them. And so MRIs and even X-rays these days and so on are getting vast amounts of scanning data and putting it together in a three-dimensional image. And even to the point where sometimes some of the stuff now, a doctor can sort of basically zoom through a person's arm and look carefully at their bones and muscles and see what's going on, and without actually having to pull the arm apart, which is quite handy if it's your arm that's in consideration. Yeah.
Tim, you are amazing at explaining things that look really complicated and making us feel like, actually, I could teach this. I can see the opportunity. So thank you so much.
Oh.
Are there any other comments, any other thoughts on computer graphics that you have? And I might just quietly stop the recording if that's okay with everyone, and we'll close with karakia.